Recall the Lebesgue density theorem saying that if you have a measurable subset of Rn, then at almost every point of the set, the balls are mostly contained in the set E. In other words, asymptotically, every point looks as if it is an interior point of the set E. It's not too surprising if I claim that the same holds for n-dimensional manifolds, submanifolds, embedded submanifolds. And here I'm assuming at least C1 regularity of a larger ambient Euclidean space. So if you have some sort of manifold of dimension n sitting in the larger Euclidean space, then when you zoom in around the point x, then the space, the neighborhood, looks as if it is an honest subset of a copy of this R little n. And therefore, the Lebesgue density theorem must hold because we talk about the case when R goes to 0. To see a more precise version of this argument, you should go to the area formula videos where we mentioned that when you have a C1 manifold, then around every point you can find a bi-Lipschitz parameterization from a subset of Rn. So you can find an open neighborhood in Rn and a parameterization of some neighborhood of that point such that this is 1 plus arbitrarily small delta by Lipschitz. So it's almost like an isometry. Therefore, Hausdorff measures of these sets and every subset of them are just almost equal up to this factor of 1 plus delta to power n. And the last ingredient would be that to remember that the Hausdorff n measure is nothing other than the Lebesgue n measure on space Rn. So it's important that this is the same. So you use this by Lipschitz parameterization actually in this direction to bring the geometry back to Rn, and then use this fact to continue. So when I said that the density theorem holds here, of course, you wouldn't take Lebesgue measure in this submanifold. You will take Hn. So it will be the case then that for almost every x, if you start with some measurable subset of m, then the ball centered at x and radius r in the manifold intersected with this E, so E is some measurable subset of m, we can say Hn measurable, divided by Wn r to power n, and taking limit as r goes to 0 would be 1 for Hn almost every x in E. So we see that the density, which is the quantity here, is well behaved when you have smooth submanifolds of a larger Euclidean space. So this is the inspiration for defining densities for arbitrary subsets and also arbitrary dimensions. So let's put that precisely. So S is a real number, 0 to infinity, so it's a finite real value. You can also include 0, but that's not interesting, it's just a cardinality. And who wants to double check every time we make a claim about densities for S also equal to 0? So we drop it from the definition to begin with. So S is some real number. E is an arbitrary subset of a big Euclidean space. No regularity assumption, nothing at all bounded, open, whatever. No assumption at all. And then we have some x in E. Then the quantities of interest will be the upper S density. So when the star is up here, you have the upper density, and when it's down here, you have lower density. So read this notation as the upper S density of the set E at point X. Actually, I wanted to emphasize that X does not need to be in E, but I did write it that way. So X is also arbitrary. So the upper density will be limit supremum as R goes to 0 of the S Hausdorff measure of a ball centered at X with radius R intersected with E divided by what would be the measure of the S measure of a Euclidean ball of radius R. Of course, if S is integer, this is really meaningful. Other than that, it's just a construct of how we have defined Hausdorff measures. So this quantity omega S diameter over 2 to power S over the coverings was what we used in definition of Hausdorff measures. So that's where this denominator comes from. So the lower density is just changing this lim sup to lim inf. So they measure by the right choice of radii. Upper density is looking for balls which are mostly contained in E, and lower density is trying to see what is the worst case that the ball does not see any part of the set E. Okay, and then if they are equal and finite, we write simply just the S density of E at X. Okay, there are a few things that I have changed from what is written in Mattila's book, which I'm using as my main resource. Number one, the denominators are different. This is because Mattila does not normalize the Hausdorff measures. He doesn't use these factors omega S over 2 to power S in front of this summation of diameters of coverings to power S. So this is not included in the definition of his Hausdorff measures, which is also a very common standard convention if you don't care about the specific quantities. So that makes him have, so he doesn't use these normalizing factors. So his denominators in definition of these densities are just 2r to power S, which is diameter to power S of the ball. And the other convention, I'm not sure about this, but he mentions that if the upper and lower densities agree, we say that the density exists. But I think it also assumes that the common value is finite as well. So maybe in the whole book, the convention is that when we say it exists, it means it's finite. But anyway, I think it's useful to add that also to the existence of density, that it is finite, as some of my examples probably will illustrate. Okay, so why define densities? The idea is that the hope is that existence of density will give us geometric. So we'll make the sets geometrically nice. So they will be less fractal-like and more like manifolds. We will see specific theorems making this precise. For example, when S is just an integer, then existence of density, that means that this upper and lower densities agree, implies that, so of course maybe there are some technical assumptions needed, so let's put quotation marks, implies that the set is rectifiable, which means it's up to a set of negligible Hausdorff measure, it's union of C1 manifolds. It's very strong claim there. Only from the existence of these locally defined quantities we obtain such restrictive conclusions about the set. So just because these densities exist, we have the fact that this set can be decomposed into a countable union of C1 manifolds, real honest C1 manifolds. Okay, so let's put down some of the ideas I just mentioned. So the questions of interest are often, so are upper and lower densities finite or positive? Well, of course you can always define them because it's lim sup and lim inf of anything exists. So the question is whether they are positive and finite. The next thing will be, when does the density exist? So are they equal? Under what assumptions on a set are they equal? And these questions will always have this part that almost everywhere. So even with the Lebesgue density theorem, you have to ignore a set of null sets. So there's no hope we can get for every single point. So it's always a question of almost everywhere. And then the thing that I just mentioned, under what conditions do densities imply rectifiability, for example, or maybe others, geometric properties of a set. Okay, so let's look at some examples, and after the examples I will state the main theorem, maybe the only general theorem that holds in all dimensions and all cases, and with future videos we will get more deeper into the study of densities. So example 1 will emphasize that when we talk about density, if you want to prove anything about these densities, their finiteness or equality, we must begin by assumption that HS of your set is finite. So this means that your set really is, number one, S-dimensional. And also, even if, okay, so because we're looking at E sitting in a much larger space, so how do you even know to look at S density and not like S prime density? Well, so this assumption here is the right indication. Also, we want it to be positive. There's not really a necessity, but if your measure is 0, then anything you claim about the set almost everywhere is true. Well, I can say at almost every point of my set, there is a neighborhood where there is a picture of a cat inside it. My claim is mathematically correct because I'm claiming it's almost everywhere true, and there are no counterexamples because the whole set E is of measure 0. So effectively, when we talk about densities, S densities, we begin with this assumption. To illustrate that further, I can give you this very specific example. So you have a sequence of parallel line segments that accumulate. So you can assume that they are at height 1, 1/2, 1/3, and so on. So they converge to this limit 1, which is also part of your set. So here is 0. So here is dot, dot, dot. Now, this is a one-dimensional set, and it's a countable union of very nice manifolds. Therefore, from all aspects, it should be among our nicest subsets, one-dimensional subsets. But when you look at the density here, if you take a neighborhood of radius r around this x, it will pick infinite line segments with a minimum length of, say, delta or r². So therefore this density 1 of E at such x will be actually equal also to the lower density, will be infinity. Because before you take r go to 0, it's already infinity, so infinity, limit of that will be infinity. So such a thing should imply, we would like this to imply that the set is not as nice as we expected. So if we did not start with this assumption, the densities would mislead us to believe that the set is a bad set. So to avoid such things, again, we add this assumption. Of course, the set E we have here is one-dimensional, but its one-dimensional measure is not finite. The next example will be that upper density, the moral will be that upper density can be strictly bigger than 1. So why is this even a thing? Because this is very different from the Lebesgue density theorem case, where because, well, the ball intersection with the set is at most as big as the ball, the fraction, even before lim sup goes to 0, r goes to 0, that fraction is never bigger than 1, so the limit is also never bigger than 1. When you're looking at S strictly less than n, and your set E is sitting in the ambient R capital N, things can change. So even with low dimensions, already we can see that in R2, you can have the set E, which is two line segments intersecting here. So if you look at the very point where they meet, and you take a ball of radius r, then you see that there are two copies of the line segment, and that will give us the upper density and lower density equal to 1 of this E at the point O is equal to 2, which is bigger than 1. And if you can do 2, why not many more? So you can have 100 of these line segments crossing each other. Can I get infinity? So of course I cannot have infinitely countably many copies of this line segment, because that would violate my beginning assumption of H1 of that set being finite. So what I then do, which is not a surprise to anyone having done anything in analysis, will be that, okay, I will have a sequence of line segments. I want to have countably many of them. But each time, let's say, each time I go into a shorter line segment, to make you believe that actually I can do such a thing, I have an angle of, say, 1 radian and a curve of length 1. And then I go to the angle 1/2, and I have the length 2 to minus 1, and then I keep doing this. Okay, I think my previous angle was too small. Okay, my lines are too thick. Okay, so I just keep going down that way. So this will be finite because this will be less than the summation of all the length of the lines, which go down by power of 2, 0 to infinity, which is equal to 2. So that's finite. Then if you take this point where all of them pass through, and you take a ball of radius r, depending on this r, many of these line segments will go from perimeter to perimeter. And if you give me, so if you give me a large M, then there exists a radius small enough so that ball of x r intersected with E has at least M copies of the diameter. So this h1 of that becomes M times the diameter, and therefore the limb sup is bigger than M. So for every M, so I must say there exist R0, so that for every R smaller than R0, because if you take a smaller R, new segments are added and never deleted. So for every M, the upper density 1, actually even the lower density of E at this point 0 is bigger than or equal to M, then it forces that the density at this point must be infinity. Okay, so this is very in contrast to the Lebesgue density theorem case where upper density was never bigger than 1. Okay, so in prediction of the theorem that I will give you by the end of this video, the question you can think about is, in the previous example, I got this bad point where density blew up at one point. Can I have it at many points? So can we have this upper density, this density of a set E, strictly bigger than 1 at a set of positive HS measure? Let me not answer this, but let's say that it is difficult to construct one. Okay, an easy way to blow up the density, as we saw, was to have an intersection. So suppose this is E. If I have a line also going vertically down at the intersection point, the density is 2 at least. So let's add just another one. Okay, that will be another point with density strictly bigger than 2. I want to have many of these, but of course, if I have infinitely many of them of comparable length, then it will violate this h1 of e less than infinity. But then I don't have to have very large ones, so I can have them at a sequence of points a1, a2, a3, and their length can be again 2 to power negative 1, 2 to power negative 2, and so on. So I can, for now, I see that I can get it for a countable sequence of intersection points with this length. Can I make it uncountable? This very particular construction, I cannot make it uncountable. So if I had uncountable points with a vertical cross, then there would exist some delta positive such that infinitely many of them, the vertical length would be of length at least delta, which would force h1 of e to be infinity. This is a very nice exercise. I've done some videos in the advanced calculus segment. If you give me uncountably many positive numbers, then there is some delta such that infinitely many of them are bigger than that delta. So if you have infimum positive, sorry, if each one is positive, then you can put a lower bound, which works for uncountably many of them. That's a nice exercise for you. So if you put uncountably many of these dots, their summation would definitely add up to infinity, even those tiny vertical segments. Okay, so that's just showing that it is difficult to come up with an example where this upper density is strictly bigger than 1. Okay, for lower density, we saw an example in constructing in discussing the Lebesgue density point, where you had this sequence of balls removed from R2, which converged to 0. And then we showed that at 0, the lower density is strictly less than the upper density. But also we had this other example, even if you don't remember this, doesn't need any background. So you have an exponentially decaying set here. So maybe this is like minus x to power 2 or something. And here is your set, which is everything between the x-axis and under this graph. Then 0 would have density equal to 0. So the density, the 2 density of this set at 0 would be 0, both upper and lower. Also, there's stupid ways of getting points of density 0. Just add a single point here to the set E. At that point, well, balls of radius R see none of the set. So again, at those points, we'll have lower density and upper density both equal to 0. And you can have countably many of them, even uncountably if it has measure 0. So it's easy to give examples where lower density and upper density become 0. But I just mentioned that you can add these points only if they have null measure. So then the question becomes, can we have this upper density S density of a set equal to 0 at a subset of HS measure positive? And that's another thing, a good exercise to think about. And this will be your last chance to think about this exercise, because I'm going to state the theorem which will give the answer to the questions I posed throughout the examples. And the theorem is as follows. Suppose you have a subset of an ambient Euclidean space with Hs of E finite. If Hs of E is 0, then the claim would actually be trivial. So the first claim is that the upper density, S density of the set E at X will be less than 1 and more than 2 to power negative S at Hs almost every point X of E. So the examples we saw above were not exceptional, but actually generic. Generically, what happens is that you cannot blow up, not really blow up, you cannot go above 1 with upper density on a significant part of any set of finite HS measure. And similarly, the upper density cannot go too low. This is saying that you have to see your set at almost every point of the set. Those points which do not see part of your set, or those points which do not contribute to the measure of the set, themselves must be of negligible measure. And part 2 says that if E is HS measurable, okay, then here rightly you're saying, wait a second, wasn't E measurable in the previous case? No, here you don't assume that E itself is HS measurable. E is not Borel, is not closed, compact, nothing. So E doesn't have to be HS measurable for claim 1 to hold. But for claim 2, you do need it. So if E is HS measurable, then the upper density of E at X is 0 at HS almost every X not in E, which also mimics what happened with the Lebesgue density theorem. If you were outside the set, then the density had to be 0. Of course, this forces the lower density, which is always less than or equal to the upper density, to be 0 as well. Okay, so two nice claims. Nice part is that they hold in this full generality. Okay, so I do plan to actually show you proofs of these, because they are among some of the most standard typical proofs in geometric measure theory, so that many future proofs or research papers or books sometimes say, okay, it follows from a standard covering argument. And what they mean, to be able to decipher that sentence, you need to have seen proofs of such theorems. So it's somehow the bread and butter of geometric measure theory, the tricks that go into proofs of these. Once you see a proof of that type, you will never forget that because it's so applicable to many other situations. So that will be some video content of some video in future. Another video will talk about this other question that we didn't give an example of. Can this lower density of a set be really strictly less than the upper density of a set on a subset of positive HS measure? Notice that the above theorem is only about the upper density in both cases. So in general, we cannot really say much about the lower density, which gives away the answer to this question that actually they don't have to be equal. And we will see examples of these also in some other future videos. It's actually easy to come up with examples. So this is given in fact as an exercise in Mattila's book. Okay, I think that's a good moment to stop here. We have talked about what densities are, what they're trying to capture. We gave examples and counterexamples. Then we stated this nice theorem. So in future, expect to see a proof of this theorem and expect to see examples and answers to the question right here at the end. But until then, have a good one and happy holidays. Keep following and commenting if you have any questions, and please consider subscribing on this very video if you like the content. Thank you so much and have a nice day.